Hydrogen, no doubt, is needed for a sustainable future, and it is an attractive energy carrier. The potential applications are wide. I do believe that one of the great opportunities for hydrogen is long-term energy storage. It also has formidable opportunities for heavy-duty mobility. As we discussed yesterday, we saw a number of very interesting presentations regarding trucks, and we'll hear more about trains. Ships, drones, and planes are all major candidates for hydrogen in the future. Hydrogen also poses significant opportunities in steel production and in agriculture, which today is the largest hydrogen users of all, because you're making ammonia and fertilizer that requires huge amounts of energy, which are not made in a green fashion today. Steel production is a major other opportunity in the future. While at Stanford we may not directly address these issues, we do believe both fields, steel production and agriculture, will benefit from many of our activities in the future. Now, there's no question in a renewable world where the primary energy sources coming from solar, wind, and other renewables, those renewables are for all practical purpose not dispatchable, which means you need to store the energy when it's available and use it when it's available to a lesser extent. We normally classify the storage needs based on the frequency response. How quickly do you have to respond to demands on the grid? And there is a very high frequency regime, which can be in the vicinity of seconds, which probably can be met by batteries. There's a more intermediate frequency of hours and days, which can be done by thermal turbines. There are significant opportunities in that domain. And then as far as long-term storage, months, even years, I see in the green domain primarily hydrogen. Of course, not necessarily pure hydrogen, hydrogen in the form of several carriers. Hydrogen may, in fact, be required to be transported from regions with lots of sun, where you have lots of solar energy cost effectively, to regions with lots of industry, and so potentially far less renewable energy available. And we will have to address the question, what is the best hydrogen carriers, whether it's metal hydrides, ammonia, hydrogen peroxide, or quite prominently synthetic fuels. There's a lot of research going on, and my colleague Tom Haramy is certainly a leader in this domain. Let me say a few words about the pros and the cons about hydrogen. Hydrogen is certainly environmentally friendly and has a fantastic gravimetric energy density, higher than many of the hydrocarbon fuels. The downside is hydrogen has a relatively low round trip efficiency. And this is depicted in the right half of my slide, which came from NREL, a government lab, the National Renewable Energy Laboratory. And you can see that the round trip efficiency when you store the energy in batteries is significantly higher than the round trip efficiency of hydrogen, where you have to first electrolyze it, make hydrogen, compress it, and then again utilize it in a fuel cell or oxidize it otherwise. But in all cases, you're losing significant, there are significant efficiency losses associated with the usage of hydrogen, and battery tends to be better. Despite all this, when you do the economics, despite the low round trip efficiency, compressed hydrogen is attractive for long-term energy storage. I'm talking about primarily from an economic point of view. It is, compared to batteries, relatively attractive long-term storage. Now, here are some of the differences between fuel cells and batteries, which I think is a good idea to briefly comment on. In contrast to a battery, a fuel cell is an open system where again it consists of a cathode, an electrolyte, and an anode. Hydrogen comes on one side, so a porous anode gets we produce protons by taking away electrons, oxidizing the hydrogen, and the protons go to the electrolyte membrane, and then on the cathode side are recombined with oxygen to make water. The electrons cannot go through the electrolyte and have to go on the outside, but this is an open system. As long as you feed hydrogen into the fuel cell will keep on running. This is not the case in a battery. A battery is a closed system. A battery will only have as much energy as you have in the active material, in the cathode material. Again, a cathode, an electrolyte, and an anode. And the cathode is the battery, the energy in the battery is limited by the cathode material available, as opposed to the open system, where as long as you feed hydrogen, you can keep on going. Now, what's the case for hydrogen for mobility? And clearly there are many pros and cons, and this is an incomplete list and subject to a lot of discussion, so I can bring up a few arguments, but this is by no means complete. Again, the main benefit of hydrogen comes from its gravimetric energy density. Hydrogen is good for long-term storage, including in mobile platforms. If you go very far and if you carry lots of load, there are some inherent advantages. Large tanks are possible, or you can also have many smaller ones. So there is ultimately will depend on the economics, and there's a potential for very fast refueling. The downside is you have a significant amount of system complexity, because every hydrogen system, every fuel cell system needs a significant battery. You need humidification, you need cooling, you need hydrogen tanks. That is one of the challenges which the fuel cell systems people need to address to deal with the complexity of the many components required for making a fuel cell system, a mobile fuel cell system work. And another inherent disadvantage is in hydrogen is the lack of existing infrastructure. The pros on the batteries is clearly have a much simpler architecture, and they can cope with a wider range of temperatures without extra heating or cooling. The downside is, again, it's, as I just said, it scales with the active material in the cathode. And no question, today's batteries are significant, have significant limitations, although this will change in a significant way in the next few years. In response to some of the advantages and disadvantages, we have seen some momentum where industry has been shifting from where the smaller vehicles or the passenger vehicles seem to have moved largely towards batteries. No question, Tesla was a pioneer in this area, but we have very fast followers all over the world. Whereas we have, I see significant opportunities on the heavy duty side, whether it's trucks, trains, or ships, drones, and so on. But we also see an interesting competition going on from pure battery electric vehicles, as we also heard yesterday, and there will be, I think, a more intense competition in the future. So clearly there has been a momentum from the smaller to the larger, because the smaller one seems to be largely dominated by battery electric vehicles when you just look at the number of produced vehicles per year. But I think there's a significant opportunity for exploring hydrogen for heavy duty applications because of the inherent advantages of hydrogen. And when you go long distances, heavy loads, consistent with what I heard yesterday, substantial system weight, where you also may need and benefit from long storage times, which inherently favors hydrogen because of its high energy density. The round-trip efficiency is a challenge for the scientific community to substantially improve. We do have, obviously, when you talk about round-trip efficiencies, there are thermodynamic limits and there are kinetic limits. The thermodynamics is normally set when you choose your material system and the overall configuration. There's not that much you can do on the thermodynamics. I always tell my students, do not fight thermodynamics, you'll lose, but there's a lot of issues you can do regarding kinetics. You can enhance the catalysis in a significant way. You can shorten the transport of various species. There's a lot of opportunities we can do, and that will have significant opportunities on the overall economics. Now, what are the research themes which we intend to address in the future? As I just said, catalysis is a big one, and it also has a significant impact because it's a key cost item. Designing and synthesizing more efficient catalytic surface structures is important both for fuel cells as well as electrolyzers. We have a lot of opportunity to explore novel hydrogen carriers ranging from synthetic fuels to ammonia, hydrogen peroxide, metal hydrides. We also need to address issues. Where are you going to transport hydrogen? If you do it in its pure form in metals, there are some challenges regarding hydrogen embrittlement, and there are also some opportunities for substantially enhancing it and mitigating some of the challenges associated with hydrogen embrittlement. There is significant opportunities to further enhance membrane design and realizing next generation membranes for charge separations, both in fuel cells and in electrolyzers, taking advantage of certain 3D structures, surface treating, synthesizing or designing hydrophobic and hydrophilic surfaces to facilitate water management. These are all significant opportunities for improving the hydrogen systems and the fuel cell and electrolyzer systems as we know it today. That all will have significant impacts on the economics, but we also need to address the overall refueling infrastructure in the future. Here are just one example on catalysis, which fits well into Silicon Valley. Here you can see the cost of the catalyst in a fuel cell, the cost of the material plus the deposition amounts to a very large fraction, over 40%, as found in a study by the Department of Energy. Now, catalysis is a surface reaction. You don't need the bulk material, you just need the surface. By depositing ultra thin layers, I'm talking about literally a few atoms, it is sufficient to function as a catalyst. And processes which were the domain of thin film production for microchips entering now the energy domain in a significant way, both in batteries and in fuel cells. And we can make surface catalyst structures taking advantage of atomic layer deposition, substantially reducing the amount of material, yet getting the same catalytic benefits. We're also studying by putting battery electric vehicles next to hydrogen electric vehicles and studying specific routes going from the west coast to the east coast or back, and then making the same recharging infrastructure, making the same renewable charging infrastructure, and evaluating what's the cost, the net present cost of the infrastructure which we need, and what's the net present cost of investing in the vehicles and investing in the actual operation to transport goods from one side of the coast to the other side of the coast. We are benefiting from a number of data in NREL, and we have our first data available on the infrastructure, which is very interesting when you compare the battery infrastructure and the fuel cell infrastructure. Finally, I would like to remark again that hydrogen has huge opportunities for steels, substantially reducing the CO2 emission. Steel accounts for almost 10% of the world's CO2 emission. And by switching to hydrogen systems, you can be substantially reduce that CO2 emission. This will take time, and this is not cheap at this moment in time, but it may even have positive impacts on the quality of the steel. We still will need some form of methane, but there are significant opportunities for hydrogen in steel production. Again, we need low cost, on demand hydrogen production. We need electrolyzers on a massive scale. And that's how our research will influence this domain as well. Same is true for fertilizer production, for agriculture. Reducing nitrogen is a major challenge. And that traditionally has been done with the Haber-Bosch process, which needs substantial amounts of nitrogen now and in the future. If you can make it in a green fashion, you contribute significantly to the environment. So in summary, it all boils down to the cost-effective production and utilization of green hydrogen, which will enable long-term energy storage, but it will also substantially create opportunities, new opportunities for mobility, heavy trucks, trains, ships, planes, drones, and it will also benefit other domains, which we probably will not address primarily in our research at Stanford. And finally, I would like to point out that hydrogen policy will be addressed, economics and infrastructure, in our new initiative in a significant way. Some of these themes and subjects will be discussed with our potential sponsors in the very near future, and many of the subjects obviously will be considered and reconsidered, and we invite our potential participants to have a lot of input on the future direction of our hydrogen initiative. Thank you very much.
We actually had a number of questions that were addressed to Professor Prinz. So the first question is regarding hydrogen fuel cells. Do you have any comments on direct burn in spark ignition of hydrogen, which if you do that, you may significantly reduce the cost?
Yes, that's inherently an attractive idea. Let's just take the infrastructure of existing engines and take advantage of hydrogen and oxidize hydrogen in the existing internal combustion engines. The downside is you're making the round trip efficiency even worse. Engines, especially mobile engines, have very limited efficiency. As you know, an IC engine, a small IC engine in a car, depending on whether it runs on gasoline or on diesel, has between 20 and 30 efficiency at best. And so you're taking overall round trip efficiency, you're bringing it further down, in contrast to a fuel cell, which has a more attractive scaling. Even when it's small, you can retain at least a 50% efficiency in energy conversion. So, which means if you go to a smaller engine, you will need even a larger tank to get the same range based on the limited efficiency.
Great, thank you, Fritz. So we have a second question, and this question is around the potential for high temperature solid oxide electrochemistry and integration to improve the cycle efficiency.
This is again a very attractive idea, because operating at high temperatures can increase your efficiency. You can also take advantage of temperature gradients and run another cycle, a temperature cycle, based on this larger gradient. The downside is stability in operation. When you run a solid oxide fuel cell at high temperatures, or even an electrolyzer at high temperatures, it takes a long time to stabilize the operation. To bring it under steady state conditions can take a long time. And the benefit of low temperature PEM-like technologies, hydrolyzer or electrolyzers, it can be done much faster. and the time to stabilize takes significantly less time. So it depends on the overall demand. If your demand fluctuates, lower temperature operations make more sense. If you have very stable demand or stable utilization, then the higher temperature can indeed benefit efficiency.